there's an old adage that says, don't meet your heroes. Well, I met one of mine and I wasn't disappointed. You can meet him too. Ladies and gentlemen, from the USA, it's Ben Shaberman.
Well, that's way too kind, Neil. It's really an honor and privilege to be here, and I want to thank all the team at Fighting Blindness Ireland for putting together what's been a really great 3 days of information on retinal conditions. So let's give them a round of applause. And today, you've heard from a lot of my heroes, the researchers, Dr. Farrar, Dr. Dinan, Dr. Keegan, and all the researchers from around the world that are doing such great work to overcome these challenging conditions. And you are my heroes, the patients and families that address and deal with these conditions with such courage and resilience. I've gained so much perspective from you and working with you that I applied to my own life. So thank you for sharing your stories and your experiences with me. In coming to Ireland, I was thinking, what can I do to really appreciate your society, your culture, your people? So I watched season 3 of The Dairy Girls, and I feel so well prepared. But seriously, I have the honor and the privilege of telling you about some of the clinical research that's underway and also some emerging therapies that are approaching clinical trials. But I wanted to start just giving you a general overview of the retina. I know you've heard bits and pieces from some of the other speakers today. And what I have up on the screen is the side view of the retina. So as I think everybody has learned, the retina is a very thin piece of tissue that lines the back of the eye. It's only a ½ millimeter thick, and it's like the consistency of wet tissue paper, so it's very fragile. But when light comes in through the front of your eye, through the vitreous, and hits the back of the eye where the retina is, the retina converts that light to electrical signals that are sent to the back of your brain, and that's how we see. Those signals your brain uses to create the images we see. And so this, again, is the side view of the retina, blown up, obviously, very dramatically. There are many layers of cells, and we sometimes call it the layer cake because it does have many layers. But the cells toward the top, those longer cells, are what we call photoreceptors, or the rods and the cones. And those are the cells that are actually absorbing light and converting light to electrical signals. And we have 2 types of photoreceptors, rods and cones. Rods give us peripheral vision and vision in dim settings. Cones, which are concentrated more into the center of the retina, give us central vision, they give us visual acuity, the ability to perceive colors and see in lighted conditions. Cones are really important for our activities of daily living. So collectively, each of our retinas has 125 million rods and cones. When I say that, I've said that many, many times over the years. It still blows me away at how powerful the retina is. Then on the right side of this slide, I have individual cartoons of a rod and a cone. That longer purple cell, lavender cell, that's a rod. The shorter green cell is a cone. And what I want you to appreciate from these images is just how sophisticated or elegant each individual rod and cone is. The top of the cell has these discs that are doing the light absorption. The bottom of the cell has all the machinery that makes the proteins that enables the cell to work. So each rod and cone is an amazing structure. And later on in my presentation, I'm going to talk about how we're harnessing other cells in the retina to make vision possible. But what's so exciting is that currently there are more than 40 clinical trials underway for emerging therapies in dry AMDs. And if you go back into the late 80s, you heard about the first inherited retinal disease gene that was discovered here in Ireland at Trinity College that Dr. Farrar mentioned. It took so many years until we started launching clinical trials, and it really wasn't until about 2006, 2007 that the first clinical trials for therapies got off the ground. And there's been this tremendous surge now in human research in trials, and again, today we have more than 40. Now, the foundation that I work for, the Foundation Fighting Blindness in the US and other groups, are working to move research to the point where we can attract outside investment from the big biotechs and pharmaceutical companies. And the reason we're doing that is clinical trials are really expensive. They cost tens of millions of dollars, in some cases hundreds of millions of dollars. But if we can move research to the point where we can attract that investment, we can get a lot more treatments through the clinical trial process and hopefully across the finish line. And I'm happy to say that model is working well. We now have dozens of companies that have invested in these rare diseases, which is extremely exciting. And again, the foundation in the US, we do a lot of different kinds of research, and we're currently funding about 90 different projects around the world. And we have funded research, Dr. Farrar at Trinity College, and we appreciate the great work that's going on there. So now I'm going to get into some of the therapies. Somebody earlier had a question about what's going on for RP. And the treatment that's, the emerging therapy that I wanted to mention next is what I call, and many of my colleagues call, a gene-agnostic therapy. It's designed to work regardless of the mutated gene causing the disease. And this particular therapy is being developed by a company called Nacuity that we're funding. They're in Dallas, in Texas. And Nacuity has developed this very strong antioxidant that's designed to slow vision loss. So in people with retinal diseases, whether it's RP, Stargardt disease, AMD, oxidative stress, the cell's inability to process oxygen in a healthy way really exacerbates vision loss. So if you can slow down or mitigate oxidative stress, you have an opportunity to save vision. So what Nacuity has done, they've taken a drug called N-acetylcysteine, which is already approved for other conditions. They've modified it to be specifically more potent and bioavailable for the retina. And they've moved it into a clinical trial in Australia for people with Usher syndrome. And this trial has now been underway for about a year. And if we get some good results in that trial, we hope to hear results in 2023. They'll move it into a trial in the US for people with RP and Usher syndrome. And we're, again, very excited about the potential of this treatment. We've invested $7.5 million in it. And again, it's gene agnostic, so it has an opportunity to help a lot of different people. So next, excuse me, I want to talk about another gene agnostic therapy that's been decades in the making. And this is a therapy specifically designed to preserve cones in people with RP, Usher syndrome, and maybe other conditions. As I mentioned just a short while ago, cones are really important for visual acuity, seeing things in the center of our visual field, for perceiving colors. And what researchers in France at the Institut de la Vision decades ago realized is that rods secrete a protein that helps keep cones alive. And what the researchers did is they designed a therapy to express this protein, and they aptly named it rod-derived cone viability factor. And they put it into a therapy. It's actually a gene therapy that expresses this protein. And they launched a company a few years ago called Sparing Vision to get this into a clinical trial. And now we're very close to Sparing Vision launching a trial for this approach. And again, it's gene agnostic. It's designed to preserve cones, to preserve central vision. And we at the foundation, we invested in this for many decades, and now we're investing at least 7.5 million euros in this company to help them get into the clinic. And the company's called Sparing Vision. Stay tuned. We hope to have news pretty soon on that clinical trial. So earlier today, you heard about X-linked RP. That's a form of RP. It tends to affect males more than females. Females are generally carriers, although there are some females that can be affected by X-linked RP, and pretty significantly. Excitingly, several years ago, some researchers at the University of Pennsylvania developed a gene therapy along with University of Florida investigators. They tested it in a canine model of X-linked RP, and that provided really great proof of concept for clinical trials of X-linked RP. And now there are 3 trials for gene therapy that's underway for X-linked RP. These trials include MIRA-GTX, which is in a phase 3. That's the trial that's underway over at Moorfields Eye Hospital. Another company called AGTC is about to launch a phase 3 trial. They're preparing for that now. And another company is at an earlier stage for their gene therapy trial for X-linked RP. They're called 4D Molecular Therapeutics, or 4DMT. So anyway, in the earlier phase of the trials for AGTC and MIRA, they observed some vision improvements for patients, and that's what inspired them to move to phase 3. And if phase 3 trials are successful, then we should get a regulatory approved treatment for X-linked RP. So very exciting work going on for this form of retinitis pigmentosa. So for people who have the most advanced vision loss, the effort to restore vision really to restore vision is pretty challenging, because by definition, people who have the most advanced vision loss have often lost all of their photoreceptors, all their rods and cones. And on the right side of this diagram, I have an X going through the photoreceptors to signify somebody who's lost all their vision because they've lost all their rods and cones. And everything I've talked about up to this point won't apply to those folks because they have no rods and cones left to save. But some very clever researchers observed that there are other cells in the retina that survive, often in people with RP and AMD, after the rods and cones are gone. And I have those cells. They're called bipolar cells and ganglion cells. Those cells are circled toward the bottom of this diagram of the retina. And what these researchers developed was a therapy that makes these cells light sensitive. Normally they're not light sensitive, but it makes them work like a backup system for rods and cones. And excitingly, this is a pretty new approach, but excitingly, it's now in 3 clinical trials. There are 3 companies that have launched phase 1/2 trials for this approach. It's called optogenetics. And the companies GenSight, Bionic Sight, and Nanoscope have all reported that people who were basically blind have had some rudimentary vision improvements. In the bionic sight trial, for example, one gentleman who had been completely blind was able to see candles during the holidays. Another person was able to see their dog running through the snow. Now, this isn't 20/20 vision, and we really don't know if optogenetics is going to bring back vision to that point. That's a pretty high bar to hurdle. But even if we can bring back some rudimentary vision for people who have lost all their vision, that would be huge. Now, some of these approaches will require special glasses or goggles to amplify the light coming into the retina. And that's because these therapies require bright light. But we're funding a company called Videre that is using a special protein that is designed to work in more normal lighting conditions where goggles will not be needed. And they're not yet in a clinical trial, but they're working toward that. So we're excited about some of the newer forms of optogenetics that are coming down the pike. So stay tuned for that. Again, this is designed for people who have lost all their vision, and it's gene agnostic. It's designed to work regardless of the mutated gene causing the disease. Now, a company we're particularly excited about that we helped launch about a year ago is called Opus Genetics. And they are a gene therapy company, and they're specifically targeting some of the retinal diseases that are rare, even among the rare retinal disease. Well, all retinal diseases are rare. These are really the rarest of the rare. And so we helped get this company off the ground. We've invested a lot of money in it. The person who, the visionary behind Luxturna, Gene Bennett, is one of our scientific co-founders. Another gentleman, Eric Pierce, at Mass Eye and Ear, a world-renowned retinal researcher who's been, or who had been chair of our scientific advisory board, is another scientific co-founder. And they're targeting 3 different gene therapies at the moment. All 3 are for LCA. They're for LCA caused by labercillin mutations, RDH12 mutations, and NMNAT1 mutations. And the goal is to launch a new clinical trial every year. The labercillin therapy, gene therapy, should be the first one. We're hoping they actually apply for the clinical trial before the end of the year. And you will see the company launch trials for conditions other than LCA. It just so happens they targeted LCA out of the gate. So Opus Genetics, targeting the rarest of the rare retinal diseases. Now, up until this point, a lot of the gene therapies I've been talking about are for delivering an entire gene to the retina to replace the mutated gene that's causing the disease. But in some cases, it may be more advantageous, instead of replacing the gene, to use what we call a cut and paste approach or an editing approach. And one relatively popular form of gene editing is called CRISPR-Cas9. And you can think of this as like molecular scissors that are used to go in and cut out the mutated area. In some cases, you may be pasting in a new tiny piece of genetic material. But again, it's editing, it's not replacing. And excitingly, a company called Editas, more than a year ago, reported results for the first CRISPR-Cas9 editing therapy that was ever applied to any part of the human body. It just so happened they targeted retina first. And they reported that for the first couple of patients treated with LCA, a specific form of LCA caused by a common mutation in CEP290, that these folks had some vision improvements. And I host a podcast. I had the pleasure of interviewing one of those participants, and he reported that his vision improved to the point where he could see the food he was eating better than previously. And the only downside, he said, to that was he was enjoying eating so much more that he was afraid he was going to gain a lot of weight. So I thought that that was a pretty promising negative statement from this young gentleman. So anyway, they've just reported results really for an early stage. We're hoping to hear more results fairly soon for more patients that have been treated. They are also developing their CRISPR-Cas9 therapy for people with mutations in exon 13 of the USH2A gene and also the rhodopsin gene, which when mutated is a common cause of RP, especially here in Ireland. So I wanted to talk about Stargardt disease a little bit and a couple of emerging therapies that are in clinical trials for Stargardt disease. Stargardt disease is a little different from RP, which we've been focused on. It causes central vision loss at first. It's caused by the accumulation of these byproducts from vitamin A processing. And you've heard a little bit about how important vitamin A is in enabling our retinas to sense light. But the challenge with vitamin A is when it is processed, there are these byproducts or metabolites that are toxic to the retina. Now, in most of us, without Stargardt disease, we clear these byproducts without any problem. But in Stargardt disease, these byproducts accumulate and cause damage. So what companies are doing is that they're trying to reduce the amount of those byproducts, those toxins, that accumulate in people with Stargardt disease. And there are a couple of companies in clinical trials with approaches that do that. One is called Alkeus, and they've developed a special form of vitamin A. It's called deuterated vitamin A that metabolizes more cleanly than the vitamin A we get from our diets. And what people in trials of this deuterated vitamin A are doing is they're reducing their consumption of vitamin A through their diet, and they're taking this modified form. And Alkeus reported in their phase 2 trial that by taking their particular emerging therapy, that it's slowing the rate of progression for people with Stargardt disease by almost 30% a year. So is it a cure? No, but if we can reduce the rate of progression by that much, we can help people preserve vision for much longer in their disease course. Another company called Belite Bio recently launched a phase 3 trial for a drug that's designed to slow the uptake or reduce the uptake of vitamin A into the retina. So if you reduce the amount of vitamin A coming into the retina, you'll have fewer byproducts, fewer of those toxic byproducts. And their trial is specifically targeting adolescents. They think that's where they're going to see the greatest effect. Now, if they have good results in adolescents, they can expand the therapy to everybody with Stargardt disease. But again, they think that's the cohort who's going to experience the greatest benefit. There are other Stargardt disease therapies in the pipeline. These are the two that we're excited about because they are in later stage clinical trials. And then finally, to close out, I did want to talk about a cell-based therapy that recently moved into the clinic for people with the dry form of age-related macular degeneration, specifically the advanced dry form called geographic atrophy. So in people with AMD, there's a layer of cells that support the photoreceptors called RPE cells. And those cells are often the first to go in people with AMD. So what this trial is doing is it's working to replace those lost and degenerating RPE cells. Now, where they're getting those RPE cells is really cool. What they're doing is they're taking a small sample of blood from the patients in the trial. They're genetically tweaking those blood cells so they revert back to a stem cell-like state, and then they're coaxing them forward to become RPE. So essentially, they're turning patients' blood into RPE cells, and they only need a small sample. The magic of stem cells is you can make them into any cell type that you need, and you can make billions and billions of cells from a small sample. So this is one of the first trials using this approach to generate cells for the retina, and the approach is called inducing pluripotent stem cells. This is going on in Bethesda, right up the road from where I live in the metropolitan DC area, and it's going on at the National Eye Institute. It's being conducted by a researcher named Kapil Bharti. So he just started dosing patients. They just started putting these cells in, so we don't have results yet. But this approach is something that other scientists are attempting to replicate, and it has promise for helping people with other retinal diseases. So that's a small sample of the research underway that's in the clinic or moving toward the clinic. I encourage you to go to the Fighting Blindness Ireland website. You can go to our website in the US, fightingblindness.org, to learn about these trials. As you heard from Dr. Dinan and Dr. Keegan, take care of your retinas, don't smoke, eat a healthy diet, get genetically tested, and thank you so much for supporting the important mission of Fighting Blindness Ireland and making the research advance. It's critical.